integral test. So this will be our first test. We're really not going to make a ton of use of this. This is going to be more of a test we use to kind of, like I said before, right? The sum of 1 over n squared converges. We're going to want to know that fact. This is the test that's going to let us know that fact, and then we'll mostly use the fact more so than the actual test. But it's still important that you know how to do it, or know how to use it. Okay, and so the idea here is that you need to have some function f, right? And then your sequence for your sum is just defined on that f, or defined as that f of n. Does that make sense? And so I'll state things a little more formally here in a little bit. But the idea is, got some point 1 here, and then here's what our f of x looks like. Okay? So we'll state things in a minute. The f needs to be positive, it needs to be continuous, and it needs to be decreasing. Okay? And so that's when this theorem is going to apply, but don't worry about the details right now. Just assume you have a series that looks like this. Okay? And so what I want to do is just draw some boxes in here. Okay? So let me do this. So if this is 1, myself some space, then that's f of 1, but by definition that's what our a sub 1 is, right? Looks like that. And then here's 2, that's f of 2, and that's what a sub 2 is, right? So remember, when we first introduced integrals, what were integrals measuring? What was the point of introducing an integral? They measured
0 to infinity.
well, so eventually we're going to do the integral from 0 to infinity, but they measured the area underneath the curve, right?
Okay.
And so the area under this curve, so the area under the curve from 1 to infinity is, right, the integral from 1 to infinity of that function, right? So we've looked at these before, and remember this was maybe the first place, well, maybe you saw it with sequences, but this might be the first place where we use the terminology convergent or divergent. Remember, if that turned out to be a finite number, we said it was convergent. If it was infinity or didn't exist, we said it was divergent. So it's the same idea here. And so what I want to do is compare this integral, or some version of this integral, some piece of this integral, with the sum. Okay? And so let me just assume I have this sum. So that sum's a1 plus a2 plus a3 and so on, right? And so all I'm going to do is draw some boxes here. What's the area of that box? It's 1, right? What's the area? Oh, not 1, but a1, right? Because you're a1 high and you're 1 wide. What's the area of the second box? a2. Area of the third box? a3, and so on, right? So what does that show us? If I add up a1 plus a2 plus a3, how does that compare to that integral? So let me just write it up here. So if I take the sum, let me write it this way. No, I'll just do this. So this is a little bit sloppy. Because again, these things, this is infinite, this has no meaning, right, the sum. But let's just assume if it's infinite, it goes off to infinity. So how does this compare with that integral from 1 to infinity? So those boxes are all sitting above that integral, right? So when I add up all the area of all those boxes, I get something that's bigger than I got when I added up, or when I integrated. Does that make sense? So I'm being a little bit informal there, but that idea hopefully makes sense. Does that seem okay? And now if we do the same thing, let's just trim off. Anybody not able to see color, purple? I don't usually ask this. Last semester, I only had colored chalk in one class, and then somebody at the end of class came up and said, I couldn't see anything you wrote because I'm colorblind, and then, for you guys, is this okay? Everybody says? So I do these boxes instead, okay? And I'm gonna erase my numbers in here. What's the size of that first purple box? Not even that, it's just A2, right? It's that height, but it's over there. And the next one is A3, A4, and so on. Does that make sense? And so now if you look at the areas again, those boxes are smaller than the integral, right? Or the area of that box should be smaller than the area under the curve. And so we get another condition here, which is this should be less than or equal to the sum, not from 1, but just from 2 to infinity. Does that make sense? And then a sub n. But it never matters what the first term was, right? You're never going to get something that's divergent by putting in some crazy first term. So this series here will converge if and only if this does, right? And since they're sandwiching this, we end up with the theorem that the convergence of this is equivalent to the convergence of that. Does that make sense? Because it's bigger than this. This converges only if this does, and so you get this sandwiching effect here. And so let me state the full integral test. So here's the theorem. The integral test. Maybe it deserves to be capitalized. Okay. So again, some initial things that I waved my hands at over there. Suppose that you have f and it's positive, continuous, and decreasing. On 1 to infinity, and a sub n equals f sub n. And let me just say, again, the integral, or the interval from 1 to infinity is sort of arbitrary. It could be the interval from 10 to infinity, depending on where your series starts. But we just want to have, and really your function doesn't need to be continuous or positive or decreasing everywhere. It just has to eventually do that, right? So you can say, you can always add up even 1 billion terms, right? And then if your function becomes continuous, positive, decreasing, then you can still apply this theorem. So just as long as that eventually happens, but we state it this way, just to make life easy. And so then the statement of the theorem is just that. This guy converges if and only if the sum of your a sub n's converges. All right. So I think the best thing, so the proof really consisted of what we did here. I won't write out any more formal thing, but I think the best thing is to just apply this to some really, really simple examples. And we'll see quickly what these look like, and then we'll hit a few sort of messier versions in a minute. Yeah. So. So there's my lazy directions, converge or diverge, okay? And so let's, the first few here, we're definitely going to use this, we're going to use this test here. So, okay. So we'll start off with some easy ones. In fact, we'll do the harmonic series again using this method in a second. But here we got the sum of 1 over n squared, okay? And so I want to apply this theorem. And so what's the function that I'm going to look at? I want the function where a sub n is f of n, so the function is just f of x, right? Or f of x is 1 over x squared, right? You convert it over to a function of real numbers from there. And so we just use f of x equals 1 over x squared. So now we have to confirm that these conditions are met, okay? Most of the time there's no work to be done. Is this a positive function? Yes, right? And we're only assuming x is, and so I'll say on 1 to infinity, right? Is this positive? Yes. So it is positive. So I want you to say it. You don't really have to show anything unless it's messy. So the only place where it's going to be messy is sometimes the decreasing isn't obvious, and so you have to do a little bit of work to show it's decreasing, but we'll talk about that in a minute. So this is positive. It's also continuous, right? The only place this is not continuous is where? 1 over x squared. It's domain. What's not in the domain of 1 over x squared? 0, right? You divide by 0. 1 over 0 squared is 0. 1 over 0 undefined. So this thing's continuous everywhere except for 0. And so definitely continuous there. And is it decreasing? Yeah, right? You're doing 1 over x squared. If you put bigger x's in, it gets smaller, right? So you don't really need to show anything. If you wanted to, you could graph it real quick and just confirm it for yourself, or use whatever method. But you want to state these facts at least, right? So you know this function is true. We check those initial conditions. This way the theorem is going to be true. And so now that sum that we're looking at will converge if and only if this integral converges. So now we just need to compute that integral. So now we compute this integral. If this converges, the sum converges. If it diverges, the sum diverges. It doesn't tell us anything about what the sum actually adds up to, right? It just tells us that it converges. Okay. So, how do we do this? Does this look familiar? Yeah. So you can, some people will just start integrating. I still want you to do it the proper way, which is to throw the limit in. Does this look familiar? Take the limit as, I'm going to use b, but you can use whatever. B goes to infinity, 1 to b. 1 over x squared dx. Okay? Now, we just let that limit sit there for a minute. What's the integral of 1 over x squared? Negative 1 over x, right? It's x to the negative 2. So integrate that and then evaluate at 1 and b. So let's just write out what that is. Right, you plug in b, you get negative 1 over b, and then minus the negative, so plus 1 over 1. Get that. What's that limit? That's 0, and then that's 1, right? So the whole thing goes to 1. And so really, we don't care what that number is. All we care about is that it converges, right? So therefore, the sum of 1 over n squared converges. And so you don't have to be crazy formal, but you need this stuff, right? You need, my function satisfied those conditions for the theorem, right? And then the theorem says that if this integral converges, then my sum converges. So this converges, and then you should say by the integral test. Does that make sense? Okay.
Would you prefer that we show all that work also on the test?
Yeah, so if this shows up, you should show this. Again, this one, 1 over n squared is one we're going to, in the next second, well, a few minutes actually, we'll know that it converges. But if, so let me just say it this way. On the test, when I want you to use the integral test, it's going to say explicitly,
use the
prove the following, or determine if the following converges or diverges by using the integral test. And so when it does, then you should show all this. But otherwise, you should almost always avoid the integral test unless I tell you to use it. It can be really useful, but it also is just pretty tedious. So let me have you try a couple of these. Same ideas. Okay. 1 over n. So we know that one does what? 1 1 plus 1/2 plus 1/3.
Diverges.
Diverges, right, it's a harmonic series. So concluded diverges, but use the integral test to show it this time. And then let's do, we'll just do the next. Okay, 1 over the square root of n. And then I think I'll just use these 3 cases to kind of state the theorem, but I'll give you, I don't know, 2 or 3 minutes to work on this. Let me know if you're having any issues with it. None.
And number C, I'm kind of struggling on the, do we have to integrate the square root in?
Right, well, so you should switch to x, but yeah.
Oh, it's at X, I know.
But 1 over the square root of x, so the square root is x to what power?
3/2.
Well, it's 1/2.
1/2.
But then since it's in the bottom, it'll be -1/2. So
Okay.
just think of it as x to the -1/2, and then just use your power rule, add 1 to the power, divide by the new power. See what you come up with.
I'm kind of confused.
Okay,
Is
so,
it-
so that's just what, right, so it should be, put the integral sign in front of there still.
Okay.
And it'll be from 1 in the bottom to b, and now you, and dx. And now integrate, so you add 1 to the power, so -1/2 plus 1 is,
3/2?
no,
Or,
-1/2 plus 1,
1/2.
just 1/2.
Okay.
So it'll be x to the 1/2 over 1/2. Change there. let's work these out together. If you haven't finished, you can finish as we go here. But it should be the same steps. So your function in this case is just what? 1 over x. Yeah, it's continuous, well, positive, continuous, and decreasing on the interval in question, right? So again, should mention that, and then you just go ahead and compute the limit. Eventually I'll let you be lazy with this limit, but for right now I still want us to do one more day of putting in this b here. So eventually these kind of things are going to be small pieces of a big problem, and so at that point you can be a little bit lazy with your notation, but for right now we should try to be careful. So what's that integral? 1 over x?
Log of x.
Log of f sine of x, 1 and b, plug in b, log of b minus log of 1 is 0. So I just have the limit as b goes to infinity of log of b, which goes to infinity. That makes sense? And so therefore, squeeze it in here. Therefore, the sum diverges on the test. Does that make sense? So in practice, if you see the sum of 1 over n, you should just say that's a harmonic series that diverges. You shouldn't do the test unless I tell you to. But at least we confirmed with another method that that works. And now we repeat the exact same thing. And so I'll go through this semi-quickly. Right? Again, you're just 1 over stuff, and so as that stuff gets bigger, it's going to decrease. And so it's positive, continuous, and decreasing on 1 to infinity. Again, then we look at that integral from 1 to infinity of that function. That's 1 over the square root of x is x to the negative 1/2. Throw in the limit here. So 1 to b, and again, it's just x to the negative 1/2. So when you add 1 to that power, you get x to the 1/2. Dividing by 1/2 is multiplying by 2, right? So you should end up with the limit as b goes to infinity of 2 square root of x, right? And then 1 and b, plug in the b, plug in the 1, you get limit as b goes to infinity of 2 square root of b minus 2. What does that do? Goes to infinity, right? And so notice the difference here when you did these two, right? This was x to the negative 2, right? So what happens when you add 1 to negative 2? You get negative 1, right? You still have a negative power. When you add 1 to negative 1/2, you get a positive power, right? And so that's the cutoff line, is this 1, right? If you take 1 over x to any power, if the power's greater than 1, you add 1, you're going to stay negative. If it's less than 1, you add 1, you'll go positive. And so that's where it cuts off between whether you converge or diverge. And so you can show it for the general case, but I think I'll just state the theorem, and hopefully these examples sort of illustrate what's going on. And I'll just put it here. We call these P series, okay? And so the series 1 over n to the p, okay? It converges if p is greater than 1 and diverges if p is less than or equal to 1. And so just like with the geometric series, how they're kind of the basic building blocks, we know which ones converge, we know which ones diverge. The same thing's going to be true with these P series. And so we're going to eventually want to have this memorized, this theorem. This is going to be, between this and the geometric series, are going to be sort of our go-to. In every other series, we're going to say, does it look sort of like a P series? Like I said before, remember we had that 1. It was like something over n squared, or n times n plus 1. And I said, well, that's going to behave like n squared. That's the sort of thing we're going to be doing here as we move forward. Is comparing everything to a series
that we already know whether it converges or diverges. So,
So this has to, you have to know that. I'm gonna put squiggly lines around it. Because once there's squiggly lines around something, you can never forget. So, hopefully that helps.
okay, let's try one more here before we get, or a couple more actually.
Same directions converge, diverge.
So, should know this fact, but actually using this is going to be something we get to a little bit later on. Okay, so determine if these converge or diverge, and I'll just tell you to be careful on that first one and think about what the last thing I said. What's the first thing we should be always doing when we determine if something converges or diverges?
I was just gonna say look at the greatest exponent and then consider the number.
Well, so I think you're onto something, you're close. Remember the nth term test said if the terms don't go to 0, the series doesn't converge, right? And so that's your first thing you should always be checking. And so even though it's in this section, if I see this, I should say, what's n squared over 3n squared plus 4 going to go to?
1/3.
1/3. So this won't converge. And so all you should do is just write that limit down, n squared, 3n squared plus 4. We're getting pretty close to the point where I'm fine with you just writing 1/3, but let me just do it at least one more time. So I don't want it to be something where you just think it's just some rule, right, that it's 1/3. It comes out to be 1/3 because all of this stuff cancels. We get 1/3. And again, all we need to conclude is this is not 0, right? Therefore, the series diverges by the nth term test. Okay? All right. Let's see. Let's do this. Now this is another one where eventually there's a better test for it than what we're going to do right now. But we're going to use the integral test on this one for now. So let's okay. We don't really need this, but so the first thing should be the nth term test. Does n over e to the n go to 0?
Yes.
Right. I agree. How would you show it if you were asked to?
Like in the numerator.
So let me come off the side. I'm going to do it with x's. If I add x over to e to the x, how would I show that goes to 0? Because what is this? This is infinity over infinity, right? So you could use L'Hopital's rule. That makes sense? And so if you do L'Hopital's rule, what do you get?
1 over x.
1 over e to the x, which is 0. Okay? So you should kind of see that. But eventually, all you want to know is, right, that exponential. So when we talk about exponential growth, what does that mean? When somebody says something's growing exponentially, I mean, it's got a formal meaning, but
a lot of times it's used sort of informally to mean something's growing fast, right? So exponential growth is really quick growth. And what we mean by it being fast is that it's faster than polynomial growth. And so anytime you have a polynomial divided by an exponential, and you're going off to infinity, that exponential will dominate it, and you'll go to 0. Or if you have that exponential up top and a polynomial at the bottom, you'll go to infinity. It's always going to take control. Okay, so now we want to use our theorem. So what are the things we need to be true to use the integral test? The function has to be positive. Is this positive? Okay. F is positive. Is it continuous? Yeah. Is it decreasing? Well, probably, because it goes to 0 and it's positive, right? I mean, but we don't know that. It's not obvious that it's decreasing. So how do you show a function's decreasing? So again, think back to Calc 1.
Yeah, larger numbers.
Well, you might be able to work it some way like that, but we have a quicker way to do it. I don't know if it's easier you need to know remember some stuff. How did you test for when functions were increasing or decreasing back in Calc 1? Throwing up the sign chart. We're doing this. Plus, minus, plus. I won't go through the details, but the point was, it was the derivative, right? You took the derivative, and whenever the derivative was positive, it was increasing. Whenever the derivative was negative, it was decreasing. So we can show this as decreasing if we just show its derivative is negative. Okay? So I'll just do that separately. So it's continuous and positive on 1 to infinity, and now let me take its derivative. Be careful here, we need to do a quotient rule, right? So we're not doing L'Hopital's rule, you're not doing derivative of the top over the bottom, you're doing the derivative of that whole thing. So, what do we get?
The U and V.
Right, so u over v, the derivative of that is derivative of u times v minus. No, you're getting ahead of yourself. I think you're talking about you're talking about integration by parts. But this is just, so let me just come off the second. Derivative, here, I'll write it like this. F over g is, right, f prime g minus f g prime over g squared. Does that look familiar? I know it's been a little while. But there's your product, or your quotient rule, right? So what's the derivative of the top? 1. So 1 times the bottom minus the top times the derivative of the bottom, which is just e to the x over e to the x squared. You may e to the 2x if you want, or you can just simplify it. I can pull an e to the x out of the top, right? And then cancel it with one of them in the bottom, and I end up with 1 minus x over e to the x. So is that negative? Yeah, it is. Once x is bigger than 1, right? You get 1 minus x. So this is less than 0 for x greater than 1. Therefore, f is decreasing on 1 to infinity. And maybe I should have picked a different example, because this is right where I said before, right? I don't really care that it's decreasing exactly on 1 to infinity. I care that it eventually decreases. So if this was, 1,000 minus x, it would be negative once you're bigger than 1,000, and that's good enough, right? Is that it eventually is decreasing. So now we're good. We can apply our theorem, and so now we have to integrate still, right? So we have to do the integral from 1 to infinity of x over e to the x. And so I'm going to do this. Right? We don't have a quotient rule for integration, and we don't have a product rule either, but we got something close to a product rule, which is the integration by parts, right? So now you have to use integration by parts on this. Maybe I'll squeeze it up in the corner. Again, this is us. We are thinking and remembering the integration by parts formula, which is what? The integral of u dv is
uv minus the integral of v du. That sound familiar? Might have been a little while. So that's what we're going to use here. So one of these parts is u, right? The other part is the dv. And so what's the choice for u here? What's the choice for dv? X should be the u, e to the negative x is your dv, e to the negative x dx. So what's du? 1, well, dx, right? 1 dx. And then v is the integral of e to the negative x, which is negative. That look familiar? And now you plug stuff into your formula here, so it becomes, again, this limit will just follow on for the rest of the problem. We'll use it at the end. So it's v, or uv, right? So that's x times e to the negative x, and negative x, e to the negative x, evaluated at 1 in b, minus the integral of v du. So what's that? Just v, right? So that's, that negative can be pulled out and canceled, so that's going to make it plus e to the negative x. Yeah, and again, keep the bounds from 1 to b. Plug stuff in. The limit as b goes to infinity. When I plug in the b, I'll get negative b, e to the negative b, and then minus the negative, so plus just 1, e to the negative 1, okay? And then the integral of this, again, is negative e to the negative x, 1 in b. So here's what I end up with. So I'm just gonna do this quickly. So this will be negative, right? It'll be e to the negative b minus e to the negative 1. So I'm going to get plus e to the negative 1. So I'll end up with 2 e to the negative 1s, and then minus b, and I'm just going to move it down, b over e to the b. Does that make sense? And then this one will just be minus 1 over e to the b when I plug in the b there. All right, so what is that limit? What's that? 0. Part of it's 0, but the 2 e to the negative 1 doesn't go anywhere, right? So that's still there. But the other two parts go to 0, right? 1 over e to the b goes to 0, and so does b over e to the b. That's that limit we just did here. And so eventually, and really at this stage, exponential grows faster than that. You should confirm or conclude that goes to 0, that goes to 0. So this whole thing just goes to 2 e to the negative 1. Point is it converges, right? And so therefore, our sum converges by that make sense? All right, so let's just say a quick word about error when you're doing this. And so so we're going to assume the same setup. Okay, we have a convergent series now. Your a sub n's are f sub n, where f is, well, positive, continuous, and decreasing on 1. And okay, and let's well, let me just write it this way. So R sub n basically gonna be the remainder. R sub n equals the sum, actually, I'm gonna follow the book. I don't remember where they want this one. Okay, we'll do it that way. So it's the n plus 1 of the a sub i's. Okay? So this is just basically adding up the tail of your series, right? Your series has a bunch of terms. This is R sub n stands for the remainder or the error that you get when you do this, and this is equal to, right, whatever your sum is. Well, let me write it this way. It's equal to, let me use k here just to be clear. K equals 1. The sum from 1 to n, that's the sum of everything, right? And I just want to add from n plus 1 off to infinity. So I can subtract off the sum from n to infinity. Wait a second. Yeah, that's right. From 1 to n. Right? So I take everything and I pull off the first n things. That's the same as adding up the tail end of it. Does that make sense? And so this is your sum of your series minus your nth partial sum. Does that make sense? So that's what the R sub n is. So R sub n, so this is equal signs flying all over the place. Let me just write it down. So R sub n is s minus s sub n. And so if you think about So the idea is we want to be able to bound how bad our error is. And so really what this is telling you is if you just add up s sub n, right, this number r sub n tells you how far off from your sum it is. And so if you know you want to get the sum, but you only need it accurate to 2 decimal places, right, you just need to find an n where this remainder, this difference is less than, well, 2 decimal places of accuracy. Does that make sense? And so, if we go back to our little boxes that we saw before, so let's have our function. In here. Right, so we got this function sitting here, and so I'm going to do it this way instead. Right, so there's a sub n plus 1, a sub n plus 2. A sub n plus 3, that's that remainder term. So we can conclude here that R sub n, which is again a n plus 1, a n plus 2, and so on. Move it over here. Well, that sum is less than the integral from n this way, right? So this is less than, let's say less than or equal to, the integral from n to infinity of your f sub x dx. Does that make sense? And so this controls how bad your sum is, how much your remainder is. I think I'm going to just leave it at that. I can't remember if I assigned any for the homework. You can just skip those for right now. If I did assign some, and we'll come back to it later on because we're going to do more error stuff later in the section, later in the chapter. So if you get to any of the error stuff, I mean, it's a nice thing to think about, but you maybe can skip it for right now.